On the morning of March 2nd, 1944, Major James Howard of the 354th Fighter Squadron stood beside his P-51 Mustang at Boxted Airfield in Essex, England, staring at what looked like an oversized tin can bolted beneath his aircraft's belly. The object in question was a drop tank, a disposable fuel container that would extend his Mustang's combat radius by several hundred miles. But this wasn't the usual metal tank. This one was made of compressed paper, flying at 25,000 feet, containing highly flammable aviation gasoline, subjected to -40-degree temperatures, violent air turbulence, and the stress of combat maneuvers. The entire concept seemed to violate common sense, yet here it was, and in approximately 90 minutes, Howard would be trusting his life to it during an escort mission deep into Germany. The ground crew chief, a grizzled technical sergeant named Robert Patterson, noticed Howard's skeptical expression. "I know what you're thinking, sir," Patterson said, tapping the tank with his wrench. It made a hollow, almost cardboard-like sound. "Looks like something we packed groceries in back home. But these things work. We've been using them for 3 months now, and I haven't seen one fail yet." Howard wasn't entirely convinced. He'd been flying fighters since 1942, first P-42s in North Africa, then P-47s over Europe. He understood fuel systems, understood the engineering that went into metal tanks. But paper? That seemed like desperation, dressed up as innovation. What he didn't understand yet, what none of the Allied pilots fully grasped that morning, was that this crude-looking paper tank represented the solution to a problem that had been bleeding American bomber crews dry for over a year. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem was brutally simple. American B-17 and B-24 bombers needed to strike targets deep inside Germany to cripple Nazi war production. But German fighter defenses were tearing the bomber formations apart. During the Schweinfurt-Regensburg raids of August 1943, the 8th Air Force lost 60 bombers in a single day, 600 men killed, wounded, or captured. The bombers desperately needed fighter escort all the way to the target and back, but no Allied fighter in 1943 had the range to accompany them. The mathematics were unforgiving. A B-17 Flying Fortress could reach Berlin from English bases, a round trip of approximately 1,300 miles. The Republic P-47 Thunderbolt, the primary American escort fighter in 1943, had a combat radius of barely 275 miles with internal fuel only. Even with external metal drop tanks, the Thunderbolt could manage perhaps 450 miles before having to turn back. This left the bombers unprotected for hundreds of miles over the most heavily defended airspace in the world. German fighter tactics evolved to exploit this gap ruthlessly. Luftwaffe controllers would track incoming bomber formations by radar and weight. They knew precisely when the American escorts would reach their fuel limits and turn back. The moment the last P-47 waggled their wings and headed home, German fighters would strike. Mi-109 and For-190 would hit the bomber formations in waves, attacking from angles calculated to maximize damage while minimizing their own exposure. The bombers had defensive machine guns, but without maneuverable fighter protection, they were easy targets. During October 1943, the 8th Air Force's daylight bombing campaign reached a crisis point. On October 14th, a mission to ball-bearing factories in Schweinfurt lost 60 bombers out of 291, dispatched a 20.6% loss rate. At that attrition level, bomber crews faced mathematical certainty of death or capture before completing their required 25 mission tours. Morale plummeted. Some crews openly questioned whether daylight strategic bombing was even possible against determined fighter opposition. The fundamental problem wasn't courage or training or tactics. The problem was fuel capacity. Fighter aircraft were weight-limited machines. Every pound of fuel you added meant less ammunition, less armor, or reduced performance. Internal fuel tanks were engineered into the aircraft's structure during design, carefully positioned around the center of gravity to maintain handling characteristics as fuel burned off. You couldn't just bolt on bigger internal tanks without completely redesigning the airframe. External drop tanks offered a solution, but they came with their own challenges. A metal drop tank was essentially a miniature fuel tank welded or riveted aluminum construction, internal baffles to prevent fuel sloshing, a pressurization system to maintain fuel flow at altitude, and attachment hardware strong enough to hold hundreds of pounds of fuel during violent maneuvers. These tanks were complex to manufacture, expensive, and heavy, even when empty. Each metal drop tank weighed approximately 60 to 80 pounds before you added fuel. More critically, metal drop tanks were meant to be recovered and reused. When a fighter jettisoned its drop tanks before entering combat standard procedure to reduce drag and weight, someone was supposed to find those tanks, truck them back to base, inspect them for damage, repair them if necessary, and prepare them for reuse. This recovery system worked reasonably well over England or friendly territory. Over Germany, recovery was impossible. Every tank dropped over enemy territory was a permanent loss. The United States Army Air Forces faced a brutal economic equation. They needed fighters with enough range to escort bombers to Berlin, a minimum combat radius of approximately 650 miles. This required external tanks holding at least 175 gallons. Metal tanks of that capacity cost approximately $125 each to manufacture in 1943 dollars, equivalent to roughly $2,000 today. If you assumed every fighter would drop its tanks over Germany on every mission, and you needed to equip several hundred fighters daily, the costs became staggering. By November 1943, procurement officers were calculating that the 8th Air Force would need approximately 15,000 new drop tanks monthly if long-range escort missions became standard. At $125 per tank, that meant nearly $2 million monthly just for disposable fuel containers, money that could otherwise buy complete fighters, engines, or ammunition. Someone needed to invent a drop tank that was cheap enough to throw away, simple enough to mass produce, and reliable enough that pilots would trust their lives to it. The solution would come from an unlikely place: the British paper industry and a chemical engineer named Frederick Banting, who'd been experimenting with compressed cellulose fiber composites for entirely different purposes. The concept of paper fuel tanks actually predated the war. British engineers had experimented with compressed paper containers for various military applications during the 1930s, including water containers and chemical storage. The material, technically called molded pressed pulp, consisted of cellulose fibers, mixed with adhesive resins and compressed under enormous pressure into rigid forms. The resulting structure was lightweight, surprisingly strong, and completely burnable if you needed to destroy evidence. When war broke out in 1939, Frederick Banting was working for Bowater Paper Corporation, developing industrial applications for pressed pulp technology. He'd created a process for molding complex three-dimensional shapes from paper fiber that could withstand significant structural loads. The military applications were obvious, but nobody initially considered using the material for aviation fuel storage. Aviation fuel was sacred. You stored it in metal tanks with proper engineering, not in glorified paper bags. The breakthrough came in early 1943, when the Royal Air Force desperately needed cheap drop tanks for Hurricane fighters being deployed to North Africa. Metal was scarce in Britain, manufacturing capacity was overcommitted, and the RAF needed thousands of tanks immediately. Someone in the Ministry of Aircraft Production remembered Banting's pressed pulp work and asked a question that seemed absurd. Could you make a fuel tank out of paper? Banting's initial response was skeptical. Aviation gasoline, 100-octane fuel with high volatility, would dissolve most adhesives. The fuel would evaporate through paper fibers. The tank would disintegrate under stress. Temperature extremes would cause catastrophic structural failure. Every engineer who reviewed the concept found a dozen reasons why it couldn't possibly work. But Banting started experimenting anyway. He developed a special resin coating that sealed the paper fibers without adding excessive weight. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. He tested different cellulose fiber combinations to find materials that maintained structural integrity when saturated with fuel. He designed internal support structures, essentially a skeleton of molded fiber ribs that distributed stress and prevented the tank from collapsing under its own weight when full. The prototype testing process was unglamorous but critical. Banting's team would fill paper tank prototypes with gasoline, then subject them to every conceivable stress. They'd drop them from heights to simulate rough handling. They'd heat them to 140 degrees Fahrenheit and cool them to -60 to test temperature extremes. They'd vibrate them for hours to simulate flight conditions. They'd pressurize and depressurize them repeatedly to ensure the paper structure wouldn't delaminate. Most prototypes failed. The paper would delaminate when cold. The resin coating would crack under vibration. The fuel would seep through microscopic gaps in the fiber matrix. But gradually, through iteration after iteration, Banting developed a manufacturing process that worked. The final design used 3 layers of specially treated paper fiber, compressed under 500 pounds per square inch of pressure, coated with a proprietary resin that sealed without becoming brittle, and reinforced with molded internal ribs that maintained structural integrity. The first operational paper drop tanks entered RAF service in mid-1943, used primarily on shorter-range missions where the consequences of failure would be less catastrophic. Pilots were understandably nervous about flying with paper tanks full of explosive fuel, but the tanks performed flawlessly. They held fuel without leaking. They maintained structural integrity through violent maneuvers. They could be jettisoned cleanly, without creating dangerous flight characteristics. And critically, they cost approximately $12 to manufacture 1/10 the cost of equivalent metal tanks. When American procurement officers learned about the British paper tanks in late 1943, they were simultaneously intrigued and horrified. The cost savings were extraordinary. The manufacturing simplicity meant production could be scaled rapidly. But American aviation culture had deep institutional skepticism about anything that seemed crude or improvised. The United States was winning the war through industrial superiority and engineering excellence, not through desperate improvisation with office supplies. Lieutenant General Ira Eaker, commanding the 8th Air Force, understood that institutional skepticism was irrelevant compared to operational reality. His bomber crews were dying because his fighters couldn't escort them deep into Germany. If paper tanks could solve the range problem, he didn't care if they were made from recycled newspapers. In December 1943, Eaker authorized testing of British paper drop tanks on American P-47 Thunderbolts. The initial tests at Bovingdon Airfield revealed immediate problems adapting British tanks to American aircraft. The attachment fittings didn't match American hardpoints. The fuel pressurization systems used different standards. The tanks were designed for British fuel types that had slightly different chemical properties than American 100-octane gasoline. But these were engineering problems with engineering solutions. Within 6 weeks, American engineers had modified the British design to work with American aircraft and fuel systems. More significantly, the arrival of the North American P-51 Mustang in European theatre service created entirely new possibilities for long-range escort. The Mustang had been designed around the Packard-built Rolls-Royce Merlin engine, a power plant that was significantly more fuel-efficient than the radial engines powering P-47 seconds. The Mustang's internal fuel capacity of 269 gallons gave it respectable range, even without external tanks. With drop tanks, it could theoretically fly escort missions anywhere in Germany. The question was whether paper tanks could handle the specific demands of P-51 operations. The Mustang flew higher and faster than Hurricanes. It operated in colder temperatures, often -50 degrees Fahrenheit or colder at operational altitudes of 25,000 to 30,000 feet. It performed more violent combat maneuvers. The paper tanks would need to survive conditions far more extreme than anything the RAF had tested. In January 1944, the 8th Air Force Material Command established a crash testing program at Wright Field in Ohio. Engineers would subject paper drop tanks to every conceivable operational stress, then examine the failures to understand failure modes. They tested tanks in altitude chambers that simulated 40,000-foot conditions, They mounted tanks on centrifuges to simulate high-G maneuvers. They filled tanks with fuel, flew them to altitude on test aircraft, then deliberately caused failures to understand what would happen if a tank catastrophically ruptured during flight. The testing revealed that paper tanks had a remarkable safety characteristic that metal tanks lacked. They failed gradually rather than catastrophically. When a metal tank developed a crack or leak, fuel would spray out under pressure, creating immediate fire hazards. When a paper tank failed, the compressed fiber structure would gradually delaminate, allowing fuel to seep slowly rather than spray. This gave pilots time to notice the problem through fuel gauge readings before reaching emergency situations. By February 1944, American manufacturers were producing paper drop tanks in enormous quantities. The manufacturing process was remarkably simple compared to metal tank fabrication. You didn't need specialized metalworking facilities, welding equipment, or skilled aviation sheet metal workers. You needed paper mills, hydraulic presses, and workers who could follow basic quality control procedures. The Barwater Corporation established the primary manufacturing facility in England at Sittingbourne, Kent, with secondary production at facilities in Ellesmere Port and Barrow in Furness. Additional production began in the United States at paper mills in Wisconsin and Maine. The manufacturing process took approximately 48 hours from raw materials to finished tank, compared to 5 to 7 days for equivalent metal tanks. The process began with cellulose fiber pulp, essentially the same material used for cardboard, but processed to much higher purity standards. The pulp was mixed with phenolic resin, adhesives, and water to create a slurry with the consistency of thick oatmeal. This slurry was poured into massive hydraulic molds shaped like tank halves, one mold for the forward section, one for the aft section. The hydraulic presses closed with 500 pounds per square inch of pressure, squeezing water from the pulp mixture while simultaneously heating the molds to 300 degrees Fahrenheit. This heat activated the phenolic resins, causing them to polymerize and bind the cellulose fibers into a rigid composite structure. After 20 minutes under pressure, the molds opened to reveal a tank half that looked like brown, slightly glossy paper, but felt as hard as wood. The tank halves were then trimmed, fitted with internal support ribs molded separately using the same process, and joined together using more resin adhesive and mechanical pressure. The seams were reinforced with additional layers of resin-impregnated paper fiber wrapped around the joint line. Once the basic tank structure was complete, it received multiple coats of fuel-resistant resin that sealed the paper fibers and prevented gasoline from seeping through. The final step involved installing the metal components: a filler neck at the top, a fuel outlet valve at the bottom, and mounting lugs that would attach to the aircraft's hardpoints. These metal components were bonded into the paper structure using specialized adhesives that created airtight seals. The completed tank weighed approximately 28 pounds empty, less than half the weight of an equivalent metal tank, and cost $12.50 to manufacture in 1944. Quality control was critical, because failure modes in paper tanks were different from metal tanks. Inspectors would examine each tank for delamination layers of paper fiber separating from each other. They'd check resin coatings for cracks or thin spots. They'd pressure test each tank to ensure it could hold fuel without leaking. Approximately 15% of tanks failed inspection and were recycled back into the pulp mixture for remanufacturing. The tanks came in several standardized sizes. The 75-gallon tank was the smallest, used primarily for shorter range missions or as wing-mounted tanks on P-47 seconds. The 108-gallon tank became the standard belly tank for P-51 Mustangs, providing the balance between fuel capacity and aerodynamic drag. The 150-gallon tank was used for maximum range missions but created significant drag penalties. And the largest variant, a massive 165-gallon tank, was manufactured in limited numbers for special ultra-long-range missions. By March 1944, production had reached approximately 30,000 paper drop tanks monthly across all Allied manufacturing facilities. This meant the 8th Air Force finally had the disposable fuel capacity to mount sustained long-range escort operations deep into Germany without worrying about tank recovery or reuse logistics. Major James Howard's mission on March 2nd would demonstrate exactly why this mattered. His target was Berlin, 625 miles from Boxted Airfield, requiring 5 hours and 40 minutes total flight time. Without external tanks, the mission would be impossible. Even with the P-51's efficient Merlin engine and internal fuel capacity, reaching Berlin required an additional 108 gallons from the belly-mounted paper drop tank. The mission briefing at 0500 hours emphasized the tactical significance. This would be the first major daylight raid on Berlin, deliberately timed to demonstrate that American bombers could strike the German capital with impunity. The psychological impact on German civilian morale would be substantial, but the tactical risk was equally substantial. Berlin sat at the absolute limit of escort range, and Luftwaffe fighter strength in the Berlin defense zone included some Germany's most experienced pilots flying the latest aircraft variants. Howard's role was straightforward: escort the bomber formation to the target area, protect them from fighter attack during the bomb run, then escort them home. The paper drop tank would get him to Berlin. After that, he'd be operating on internal fuel only, which meant approximately 90 minutes of combat time before he'd need to turn back toward England. 90 minutes to protect bombers, engage German fighters, and survive long enough to make it home. At 0645, Howard's P-51 lifted off from Boxted, the paper tank heavy beneath the fuselage, creating noticeable drag during the initial climb. The tank held 108 gallons of gasoline, 648 pounds of additional weight that made the Mustang feel sluggish and ponderous compared to its usual razor-sharp handling. But that weight was also range. Each gallon represented approximately 4 miles of additional flying distance. The formation assembled over England at 12,000 feet, 56 P-51 Mustangs from the 354th Fighter Group, joining with hundreds of other fighters from multiple groups. Together they would escort 3 bomber divisions over 600 B-17 flying fortresses to Berlin and back. The bomber stream stretched for miles, an aerial armada that represented the largest daylight raid on the German capital in history. As the formation climbed toward operational altitude, Howard monitored his fuel gauges carefully. The paper tank fed first, before internal tanks, which meant he was currently burning fuel that would be thrown away once the tank emptied. The gauge showed full 108 gallons of high-octane gasoline sloshing inside compressed paper fibers, held together by resin and prayer, keeping his Merlin engine running at 2200 RPM. The flight across the North Sea was uneventful. Howard's flight, 4 P-51 seconds flying in finger 4, formation maintained position on the bomber stream's right flank, weaving gently to maintain the slower bomber's speed without stalling. At 18,000 feet, outside air temperature dropped to -30 degrees Fahrenheit. Howard wondered briefly if the paper tank would become brittle in the extreme cold, if the resin coating would crack, if fuel would start streaming from 1,000 microscopic fissures in the paper structure. But the fuel gauge remained steady. The engine continued running smoothly. The paper tank was doing its job, even at -30 degrees, even at altitude, even under conditions that would have seemed impossible in any laboratory test. By 0900 hours, the formation crossed into German airspace near Oldenburg. Fuel consumption from the drop tank was tracking exactly as planned. Howard calculated he'd empty the paper tank approximately 20 minutes before reaching Berlin, which would leave him with full internal tanks for combat operations. The timing was critical. You wanted to jettison drop tanks before encountering enemy fighters, because the empty tanks created enormous drag and made the aircraft vulnerable. At 0920, Howard's drop tank gauge reached empty. He verified the internal tanks were feeding properly, then pulled the emergency release handle. The paper tank separated from the belly hardpoint cleanly and tumbled away, falling toward German farmland 30,000 feet below. Howard would never see that tank again, neither would anyone else. Unlike metal tanks that would remain intact after impact and potentially be recovered by German forces for analysis, the paper tank would disintegrate on impact, scattering into thousands of pieces of unidentifiable debris. This was another advantage of paper construction that military planners appreciated but rarely discussed publicly. Paper tanks were essentially self-destroying, if they survived the fall, which was unlikely given their relatively fragile. construction they'd dissolve in rain within weeks. They couldn't be captured, analyzed, or reverse-engineered by enemy forces. They were intelligence-proof by virtue of being disposable garbage. Without the drag of the empty tank, Howard's Mustang immediately felt lighter and more responsive. He advanced the throttle slightly, feeling the aircraft accelerate smoothly. Now he was flying on internal fuel, only 184 gallons remaining in fuselage and wing tanks. Enough for approximately 2 hours of combat operations, then the long flight home. The Luftwaffe hit the bomber formation at 09:45, approximately 80 miles west of Berlin. German fighter controllers had tracked the raid by radar since the formation crossed the coast, calculating intercept vectors and positioning fighter groups for maximum effect. The initial attacks came from Mi-109G6 variants diving from altitude, trying to separate bombers from the protective fighter screen. Howard's flight engaged immediately, turning into the German fighters and climbing to meet them. The dogfight developed rapidly into the chaotic furball that characterized high-altitude combat aircraft twisting through three-dimensional space at closing speeds exceeding 600 miles per hour, each pilot trying to achieve firing position while avoiding becoming a target himself. What happened over the next 40 minutes would earn Howard the Medal of Honor, the only fighter pilot in the European theater to receive the decoration for a single mission. When his flight became separated from other friendly fighters, Howard found himself alone protecting a formation of B-17 seconds from attacks by approximately 30 German fighters. Rather than withdrawing or calling for help, he attacked. For 40 minutes, Howard engaged German fighters single-handedly, destroying at least 3 confirmed and damaging several others. He would dive on attacking fighters just as they committed to their firing runs on bombers, forcing them to break off. He'd climb back to altitude, position himself between bombers and the next wave of attackers, then dive again. He flew with absolute aggression, trading ammunition for time, buying minutes for the bomber crews by making himself the more attractive target. His Mustang absorbed battle damage 20 millimeters, cannon shell fragments punctured his right wing, machine gun bullets stitched his fuselage, his canopy cracked from a glancing hit, but the aircraft kept flying. The Merlin engine, already proven reliable in British service, maintained power throughout despite flying at maximum continuous output far longer than recommended limits. By 10:30, Howard's ammunition was exhausted. He'd fired all his .50 caliber rounds engaging German fighters. But he continued flying aggressive attack patterns, diving on German formations as if he still had ammunition, bluffing them into breaking off their attacks on the bombers. The German pilots couldn't know his guns were empty. They had to assume each aggressive move represented lethal threat, so they reacted defensively, wasting time and fuel maneuvering against a fighter that could no longer shoot. At 10:45, the bomber formation completed its run over Berlin and turned for home. German fighter attacks had been fierce, but relatively ineffective. The bomber losses were far lower than pre-mission estimates, partly because fighters like Howard had prevented German fighters from achieving sustained firing positions. The first raid on Berlin was a tactical and propaganda success. Now came the difficult part. Getting home. Howard's fuel gauges showed 78 gallons remaining in internal tanks. The return flight to England would require approximately 2 hours at economical cruise settings. His navigation calculations suggested he had enough fuel, but the margin was thin, perhaps 15 minutes of reserve. There would be no maneuvering for position, no deviations from the direct route, no allowance for strong headwinds or navigational errors. The paper-drop tank that had brought him to Berlin was gone, disintegrated somewhere over northwestern Germany, but it had done its job perfectly. It had carried 108 gallons of fuel without leaking, without structural failure, without any of the catastrophic problems that skeptics had predicted. A $12 compressed paper container had enabled a mission that changed the strategic air campaign over Europe. The strategic transformation that paper-drop tanks enabled became apparent within weeks of their widespread deployment. Throughout March and April 1944, the 8th Air Force mounted sustained, deep penetration raids against targets that had been previously untouchable. Berlin, Leipzig, Augsburg, Munich cities that sat beyond the effective range of metal tank-equipped fighters suddenly found themselves under regular attack by formations, escorted all the way to target and back. German fighter losses escalated dramatically. Luftwaffe pilots who had grown accustomed to attacking bombers in the dead zone beyond fighter escort range now faced continuous fighter opposition throughout entire missions. The tactical advantage shifted decisively. Instead of German fighters choosing when and where to engage, American escort fighters could maintain persistent presence, forcing the Luftwaffe to fight on Allied terms or concede the airspace entirely. The mathematics of attrition turned against Germany. A Luftwaffe pilot who survived his first 20 combat missions in early 1943 had reasonable odds of surviving 50 or even 100 missions. By mid-1944, with American fighters roaming freely over Germany, pilot survival rates plummeted. Experienced pilots died faster than the training system could replace them. Aircraft production continued, but pilot quality declined as training programs shortened under pressure to fill gaps in frontline units. Reichsmarschall Hermann Göring, commanding the Luftwaffe, reportedly became obsessed with understanding how American fighters had suddenly gained such extraordinary range. German intelligence conducted extensive analysis of crashed American aircraft, interviewed captured pilots, and examined every available piece of technical documentation. They knew about drop tanks. The Luftwaffe used metal drop tanks on its own fighters, but the range figures didn't make sense based on known American metal tank capacities. In April 1944, German forces recovered an intact paper drop tank near Brunswick after an American fighter jettisoned it during combat. The tank had survived impact relatively intact, unusual, but possible if it landed in soft ground at the right angle. German intelligence officers transported it to the Luftwaffe testing facility at Rechlin for analysis. The technical assessment report, declassified decades after the war, reveals the German reaction. Engineers at Rechlin literally could not believe the tank was made of paper. Initial analysis assumed it was some kind of advanced composite material, perhaps phenolic resin reinforced with fabric, or an early form of fiberglass. When chemical analysis confirmed the primary material was compressed cellulose fiber paper, the German engineers concluded the tank must be for short-range use only, perhaps carrying water or non-flammable liquids. The concept that Americans were using paper tanks to carry aviation gasoline on 5-hour combat missions violated German engineering sensibilities. Paper was not an aviation material. Paper was what you used for documents, for packaging, for temporary applications where structural integrity didn't matter. Using paper for critical aircraft systems seemed like either brilliant deception or American technical incompetence. The Rechlin report acknowledged the tank's lightweight and simple construction, but emphasized numerous theoretical failure modes. The paper structure would delaminate under vibration. Temperature extremes would cause catastrophic structural failure. The material would dissolve when exposed to aviation fuel. Combat damage would cause immediate rupture and fire. The report concluded that widespread deployment of such tanks would be impossible for serious military operations. This assessment perfectly illustrated a fundamental difference in German and American engineering philosophy. German aviation engineering emphasized precision, advanced materials, and technical sophistication. The Messerschmitt Me 262 jet fighter, entering service in 1944, represented the cutting edge of aviation technology: swept wings, axial flow jet engines, advanced aerodynamics. It was a masterpiece of engineering that required specialized manufacturing facilities, exotic alloys, and highly skilled labor. American engineering emphasized mass production, standardization, and practical solutions over technical elegance. The paper drop tank embodied this philosophy perfectly. It wasn't sophisticated, it wasn't impressive to examine, but it worked. It was cheap, and you could manufacture 30,000 of them monthly, using relatively unskilled labor in facilities that didn't require specialized equipment. In a war of industrial attrition, cheap and functional beat sophisticated and scarce. German industry never attempted to replicate paper drop tanks, despite the obvious advantages. Partly this reflected institutional skepticism. If German engineers said paper tanks wouldn't work, then they wouldn't work, regardless of evidence that Americans were using them successfully. But it also reflected Germany's increasingly desperate resource situation by mid-1944. The German aviation industry was struggling to maintain aircraft production under constant Allied bombing, factories dispersed to underground facilities, supply chains disrupted, skilled workers conscripted into military service. Introducing an entirely new manufacturing process for drop tanks, even a simple process required resources that Germany couldn't spare. Existing metal drop tank production continued, supplemented by increasingly crude field-expedient designs, but never matched Allied production volumes. Meanwhile, Allied paper tank production scaled exponentially. By June 1944, the month of the Normandy invasion, monthly production exceeded 50,000 tanks across all Allied manufacturing facilities. The Bowater plants in England operated 3 shifts daily. American paper mills in Wisconsin and Maine converted entire production lines to military use. Even smaller facilities in Canada and Australia began producing tanks to support Pacific theater operations. The production process became increasingly refined. Early tanks required 48 hours from raw materials to finished product. By mid-1944, streamlined manufacturing reduced this to 32 hours. Quality control improved through experience. Manufacturers learned to identify problematic batches of resin, developed better testing protocols, refined the molding process to reduce defects. Rejection rates dropped from 15% to under 8%. The tank's operational characteristics improved through iterative design changes. Engineers discovered that adding reinforcement ribs in specific locations reduced flexing during high-G maneuvers. Modified resin formulations improved cold weather performance. Better mounting hardware reduced instances of premature separation. These improvements emerged from systematic analysis of field performance reports, pilots and ground crews reporting problems, engineers developing solutions, manufacturers implementing changes within weeks. This rapid improvement cycle reflected another American advantage: institutional flexibility. When British pilots reported that paper tanks occasionally developed leaks during prolonged cold weather operations, engineers identified the problem, the resin coating became brittle below -40 degrees, and reformulated the coating within 6 weeks. New production incorporated the improved resin immediately, and existing stock received additional protective coatings before deployment. German aviation industry, by contrast, struggled with rigid bureaucratic structures that slowed innovation. Proposed design changes required extensive documentation, committee reviews, and approval from multiple agencies. The time between identifying a problem and implementing a solution often stretched to months or years. In a rapidly evolving air war, this institutional sclerosis proved fatal. The P-51 Mustang, equipped with paper drop tanks, achieved combat radius figures that seemed impossible when the war began. A standard mission profile: climb to altitude, cruise to target area 600 miles distant, engage in combat for 30 minutes, return home required approximately 350 gallons of fuel total. The Mustang's internal capacity of 269 gallons, supplemented by a 108-gallon paper belly tank, provided 377 gallons. This gave pilots a comfortable reserve for combat maneuvering, weather diversions, or navigational errors. Maximum range missions used larger tanks and careful fuel management. With a 165-gallon belly tank, plus 2 75-gallon wing tanks, a Mustang could achieve combat radius exceeding 850 miles. This meant fighters based in England could escort bombers to targets in Czechoslovakia, southern Germany, or western Poland. No part of Nazi-controlled Europe remained beyond reach of American fighters. The longest combat mission, flown by P-51 seconds using paper drop tanks, occurred on September 11, 1944, when fighters from the 352nd Fighter Group escorted bombers from England to industrial targets near Chemnitz, Germany, a round trip of approximately 1,400 miles, requiring 6 hours 40 minutes total flight time. Every fighter carried maximum fuel load, including the large 165-gallon belly tank and 2 wing-mounted 75-gallon tanks. 28 fighters launched on that mission. 26 returned safely to England. The two losses resulted from combat damage, not fuel exhaustion. Post-mission analysis showed that returning aircraft had fuel reserves averaging 12 to 15 gallons, roughly 20 minutes of flying time. The mission pushed the absolute limits of Mustang range, but it demonstrated conclusively that American fighters could operate anywhere over occupied Europe. German defenders faced an impossible situation. They couldn't concentrate forces at any single defensive point, because American fighters could escort bombers to any target. They couldn't wait for fighters to reach fuel limits and turn back, because the fighters now had enough fuel to escort bombers throughout entire missions. They couldn't achieve air superiority over their own territory, because they were consistently outnumbered by attackers who held initiative and chose engagement terms. Luftwaffe defensive doctrine adapted out of desperation. By autumn 1944, German fighters increasingly avoided engaging American escorts entirely, instead focusing exclusively on bombers and accepting heavy losses in exchange for any successful attacks. This tactical choice reflected grim calculation. A pilot who destroyed one bomber before being shot down himself achieved a favorable exchange ratio, since bombers carried 10 crew members versus one fighter pilot. But even this desperate approach failed strategically. American bomber production vastly exceeded losses. For every bomber destroyed over Germany, American factories delivered 4 new bombers to England. The 8th Air Force could sustain loss rates that would have crippled the Luftwaffe. Meanwhile, German aircraft production, despite reaching peak output in late 1944, couldn't replace combat losses plus the accelerating attrition of experienced pilots. The paper drop tank had become, quite literally, disposable strategic advantage. Each tank enabled a combat mission that might destroy tens of millions of dollars worth of German industrial capacity while forcing the Luftwaffe to commit irreplaceable fighters and pilots. The return on investment was extraordinary by any measure. Pilots' attitudes toward paper tanks evolved from skepticism to casual acceptance. By late 1944, fighter pilots no longer questioned whether paper tanks would work. They simply assumed each mission would include whatever combination of paper tanks provided required range, and that the tanks would perform flawlessly. Ground crews developed efficient procedures for installing and removing tanks. A 4-man crew could mount a belly tank in approximately 12 minutes. The tank's disposable nature paradoxically increased pilot confidence. With reusable metal tanks, pilots worried about damaging expensive equipment through hard landings or rough handling. With paper tanks, there was no concern about damage. If a tank developed problems before takeoff, ground crew would simply unbolt it, throw it away, and mount a new one. The entire replacement process took less time than inspecting and repairing a metal tank. Combat damage sometimes revealed the tank's paper construction in dramatic fashion. Several pilots reported instances where enemy fire struck drop tanks, causing them to disintegrate into clouds of paper fragments rather than exploding or burning. The compressed paper structure would simply come apart, scattering pieces across the sky while the fuel dispersed harmlessly as vapor. This failure mode was significantly safer than metal tank rupture, which often caused catastrophic fires. Lieutenant Robert Johnson of the 56th Fighter Group survived an encounter in June 1944 that illustrated this characteristic. While escorting bombers near Magdeburg, his P-47 Thunderbolt took cannon fire from an Me-109 that attacked from below. A 20mm shell struck his belly-mounted paper drop tank directly. Johnson felt the impact, saw the tank disintegrate through his mirror, but experienced no fire or explosion. The tank simply came apart into thousands of pieces of paper and resin, the fuel inside dispersing as mist. Johnson jettisoned what remained of the mounting hardware and continued his mission. Had that same shell struck a metal tank, the results would likely have been catastrophic. Metal tanks, when punctured by high explosive rounds, typically ruptured violently. The combination of fuel vapor, explosive shell, and confined space inside a metal container created ideal conditions for devastating fireballs. Johnson's survival was partly attributable to the fragile nature of compressed paper construction. By the end of 1944, Allied air forces had consumed over 400,000 paper-drop tanks across all theatres. The vast majority, perhaps 75%, were jettisoned over enemy territory and never recovered. They fell into German fields, French forests, Italian mountains, and disappeared. Some were recovered by curious civilians who had no idea what they'd found. Most disintegrated from weather exposure within months, dissolving back into their component materials. This disposability represented strategic benefit that extended beyond simple economics. Each jettisoned tank required no recovery logistics, no return shipping, no inspection and repair cycle. The supply chain was one way: manufacture, ship forward, use once, discard. This simplified logistics dramatically compared to reusable metal tanks, which required complex reverse logistics to collect, transport back to depots, inspect, repair, and redistribute. The administrative burden alone was significant. Metal tank logistics required tracking individual tanks through serial numbers, maintaining maintenance records, coordinating recovery from scattered airfields, and managing repair facilities. Paper tank logistics required only inventory counts and forward shipping. When a fighter group needed more tanks, you simply shipped a truckload from the depot. No serial numbers, no paperwork, no accountability beyond counting how many tanks you had versus how many you needed. German intelligence officers, examining captured documents after the war, discovered just how thoroughly paper tanks had enabled Allied air superiority. Internal Luftwaffe memoranda from late 1944 acknowledged that American fighters' extended range had rendered German defensive strategy obsolete. One report, dated November 1944, stated bluntly, "The enemy now possesses fuel capacity that permits fighter escort to any target within the Reich. Defensive concentration of forces at predicted target areas no longer provides advantage, as the enemy can maintain continuous fighter presence throughout penetration and withdrawal phases." The report's author, a Luftwaffe staff officer whose name was redacted from declassified versions, recommended abandoning daylight operations entirely and concentrating remaining fighter strength on night interception of British bombers. This recommendation was partially implemented in December 1944, but by then the strategic situation had deteriorated beyond recovery. Germany lacked the fuel, the pilots, and the aircraft to contest Allied air superiority, regardless of tactical doctrine. Post-war analysis by the United States Strategic Bombing Survey examined the paper-drop tank's contribution to Allied victory. The survey's aviation section concluded that paper tanks, combined with the P-51 Mustang's fuel efficiency and performance, decisively shifted the air superiority balance over Europe, beginning in spring 1944. The report noted that German aircraft production actually increased through late 1944, but became strategically irrelevant because the Luftwaffe could no longer effectively defend German airspace. The economic analysis was equally striking. The survey calculated that paper-drop tanks cost Allied forces approximately $5 million total to develop, manufacture, and deploy in the quantities used during 1944 and 45. The strategic value generated measured in destroyed German industrial capacity, degraded Luftwaffe effectiveness, and reduced bomber losses exceeded billions of dollars in contemporary valuation. Few weapons systems in history achieved comparable return on investment. Major James Howard, whose Medal of Honor mission over Berlin demonstrated paper tanks' capabilities, survived the war and returned to the United States in October 1945. In post-war interviews, he frequently emphasized the mundane reality of technological advantage. "People ask about the exotic stuff," he said during a 1952 interview preserved in Air Force archives. "They want to hear about jet engines and guided missiles and radar. But what actually won the air war was simpler than that. We had enough fuel to stay with the bombers all the way to target and back. The Germans didn't have answers for that because it wasn't a problem you could solve with advanced technology. It was a problem of industrial capacity and practical engineering." Howard never flew with metal drop tanks after March 1944. Every subsequent mission used paper tanks exclusively. He accumulated over 100 combat missions before war's end and never experienced a paper tank failure. "They looked ridiculous," he recalled. They felt flimsy when you touched them on the ground, but at 25,000 feet over Germany, carrying fuel that kept your engine running when you were 300 miles from home, they worked perfectly. That's all that mattered. The paper drop tank story reveals an uncomfortable truth about technological warfare. Sophistication doesn't guarantee victory, and crude solutions sometimes outperform elegant ones. German engineers built technically superior aircraft, designed advanced engines, and developed weapons that represented cutting-edge aviation technology. But they lost the air war to an opponent who mass-produced adequate aircraft supported by disposable paper fuel tanks. This outcome challenged deeply held beliefs about engineering excellence and military effectiveness. The Luftwaffe entered the war convinced that superior technology and pilot skill would overcome numerical disadvantages. By 1944, they faced an opponent whose advantages weren't primarily technological. American fighters weren't necessarily better aircraft than German fighters, though the P-51 was excellent by any measure. American pilots weren't necessarily more skilled than German pilots, though training and experience mattered enormously. The American advantage was industrial, the ability to produce overwhelming quantities of adequate equipment, supported by innovative solutions like paper drop tanks that reduced costs and simplified logistics. This approach didn't make for dramatic stories of technical breakthroughs or revolutionary weapons. It made for victory through systematic application of industrial capacity to military problems. Frederick Banting, the chemical engineer whose pressed pulp technology enabled paper tank production, never received public recognition during his lifetime. He continued working for Bowater Corporation after the war, developing commercial applications for molded paper products. He died in 1957, relatively unknown outside specialized industrial engineering circles. His obituary in the London Times mentioned his wartime work in a single sentence, noting that he'd contributed to various military applications of pressed paper technology. The production facilities that manufactured hundreds of thousands of paper drop tanks during the war returned to commercial production within months of victory. The Sittingbourne plant resumed making paper packaging. The Wisconsin and Maine mills went back to producing industrial paper products. The specialized knowledge of fuel-resistant resin formulations and high-pressure molding techniques found applications in early plastics industry, automotive components, and consumer products. By 1950, paper drop tanks had largely disappeared from military service. Jet aircraft required different fuel tank designs suitable for high speeds and altitudes. The Cold War drove aviation technology toward aluminum and composites, materials that could withstand the extreme temperatures and stresses of supersonic flight. The paper drop tanks moment had passed, relegated to historical footnotes and obscure technical documents. But in museums and archives, a few examples survived. The National Museum of the United States Air Force in Ohio displays a paper drop tank alongside a P-51 Mustang, explaining its role in the European air campaign. The Imperial War Museum in London holds several examples in storage, occasionally bringing them out for special exhibitions. These surviving tanks look exactly as skeptical pilots described them in 1944, like oversized paper bags, crude and temporary, utterly unimpressive. Touch one of these museum pieces and you'll feel the compressed paper structure, still surprisingly rigid after 80 years. Look closely at the resin coating, yellowed and cracked with age but still intact. Read the faded stenciling that indicates capacity and manufacturing date. And understand that thousands of these unremarkable objects changed the course of World War II by solving a problem that sophisticated engineering couldn't address. The Germans never expected compressed paper to give Mustangs 2,080-mile combat range because it violated their assumptions about proper engineering. They believed aviation systems required sophisticated materials, precision manufacturing, and technical elegance. They were wrong. Sometimes the winning solution is the one that works well enough, costs little enough, and can be produced fast enough to deploy at scale. Major Howard understood this instinctively. So did the pilots who flew mission after mission with paper tanks bolted beneath their aircraft, trusting their lives to compressed cellulose fiber and phenolic resin. So did the engineers who designed the tanks, the workers who manufactured them, and the logisticians who shipped them forward to be used once and thrown away. The paper drop tank wasn't elegant, it wasn't impressive. It wasn't the kind of technological achievement that captures imagination or generates headlines. It was simply a cheap, disposable solution to a critical problem, implemented at scale by an industrial system that valued practical effectiveness over engineering sophistication. And that made all the difference. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.